Welcome to Numerical Methods for Scientists and Engineers with Pseudocodes. Video 4. Cubic Spline Interpolation. A major problem with polynomial interpolation is that it often leads to unacceptably inaccurate estimates. When dealing with a large number of data points, we commonly encounter Runge's phenomenon. Thus, interpolation with a single polynomial covering the whole data range is generally not advised. Alternatively, low-order piecewise polynomials can be employed throughout the data range to avoid Runge's phenomenon. Because only low-degree polynomials are used, the problem of overfitting or excessive oscillations is eliminated. A function composed of low-order piecewise polynomials is frequently referred to as a spline. A data point where two splines are joined is called a knot. Conventionally, a data interval is divided into more than one interval, where a linear, quadratic, or cubic polynomial is employed for each interval. In this respect, spline methods present a different approach than the polynomial interpolations covered so far. The simplest spline method is a linear spline, where two data points are joined by a line. Cubic splines can be joined in different ways to produce an overall interpolating curve. We consider non-uniformly spaced data and employ a cubic polynomial ykx, which has a different set of coefficients for each interval, from xk to xk plus 1. Each cubic polynomial is joined to its neighboring cubic polynomials, yk minus 1, yk, and yk plus 1x, at the knots by matching the slopes and curvatures, e.g., y prime and y double prime x. Once the coefficients of the cubic polynomials are obtained, these piecewise polynomials are valid in the interval that they are specified. Consider a non-uniformly spaced discrete dataset. A cubic polynomial that will be imposed on n-1 intervals is expressed for the kth interval as follows. The distribution of data points, cubic splines, are illustrated in this figure. For each interval between two adjacent data points, cubic spline interpolation fits a cubic polynomial. The cubic polynomials for each interval are written as follows. This system consists of n-1 cubic polynomials as the number of intervals and 4 times n-1 unknowns, which are the coefficients of the cubic polynomials, i.e., a, b, c, and d's. Continuity of the function requires that the cubic splines are continuous at interior knots. That is, interpolating polynomials must satisfy the data points. From the continuity condition, we find n-1 equations, or dk's, that are equal to the ordinates. And the continuity of splines leads to the following equation, where delta xk denotes x, k plus 1, minus xk. Continuity of the first derivative at the interior knots leads to the following equation, where and from the slopes at the knots from the right-hand and left-hand sides, we get the following equation, which gives 3 times n-1 equations, that is, ak, bk, and ck's for k equals 1 through n-2. The continuity of the second derivatives at interior knots leads to the following equation. We also have the second derivative as follows. Since y double prime of a cubic polynomial gives a linear relationship, its distribution on the interval from xk to x, k plus 1, must also be linear, defining sk equals y double prime x, k plus 1, k from 1 through n-1. Which gives the cubic spline coefficients in terms of sk's. we have introduced additional unknowns, namely the SKs. To determine the curvatures at the knots, we substitute the coefficients of the polynomial. Rearranging gives the following relationship. This expression gives the relationship between the curvatures of 3 consecutive knots. To have n times n linear equations, SKs as unknowns, we need 2 more equations. Several spline formulations can be developed through the curvature estimations referred to as end conditions. The 2 equations are supplied by estimating the curvature at the endpoints of the data range. Here, we consider 2 cases only: natural splines and linear extrapolation end conditions. The discrete data is assumed to have inflection points at x equals x1 and x equals xn, where y double prime for x1 and xn is 0. Since Sx is defined as y double prime x, likewise, S1 and Sn are set to 0. This leads to the following tridiagonal system of linear equations for S2 through Sn-1, where the right-hand side and diagonal elements are defined as follows. We now apply linear extrapolation end condition to the left end. Since the second derivatives of cubic splines are linear, the endpoint curvatures are estimated by linear extrapolation. The linear extrapolation for the knot number 2 yields. Substituting S1 into the equation derived for k equals 2 in the general expression gives the following equation. Applying the linear extrapolation for the knot number n-1 gives. Similarly, substitution into the general expression with k equals n-1 results in the following equation. Upon employing an end condition, S2 through Sn-1 are found from the solution of the system of linear equations. A set of n-1 coefficients are computed for an interval from xk to xk plus 1, as follows. A cubic spline interpolant constructed by implementing any end condition is unique. The uniqueness of the interpolants allows us to estimate the approximation errors, or error bounds, associated with cubic splines by the polynomial approximations, i.e., the absolute error bounds for the cubic splines are given by the following expression, where h is the maximum interval size. This expression indicates that if h is sufficiently small, the order of the interpolation error will be 4th order. The order of error for the cubic splines method with linear extrapolation is 4th order as h goes to 0, whereas the maximum error for the natural spline end condition is 2nd order. The advantages of the cubic splines are: the method provides stable and smooth interpolating polynomials. Once the cubic spline coefficients are determined, not only y but also y prime and y double prime derivatives can be easily estimated at low cost. The cubic spline algorithm with a linear extrapolation end condition generally gives better results. Non-physical oscillations associated with Runge's phenomenon are not observed. The disadvantages of the cubic splines are: since the curvature of the distribution at the endpoints is critical, the method may not produce a proper interpolation curve if the end conditions do not suit the true curvature. Splines are not suitable for extrapolation operations, and the method is a bit more computationally involved in comparison to linear splines. As an example problem, we consider the following discrete dataset, for which we will derive the cubic spline coefficients using the linear extrapolation end condition and estimate f1.2, f2.1, and f2.9. The true function is given as follows. To calculate the cubic spline coefficient, we need to solve the problem for the second derivatives, that is, for sk's. Note that the data set is uniformly spaced with the interval size of 0.5, which greatly simplifies the equations. We need the forward differences, i.e., delta fk's. The computed results are tabulated in the presented table. Equation 6.58 for uniform intervals yields. Likewise, equation 6.59 results in. For uniform H, equation 6.51, which gives the relationship between the curvatures of 3 consecutive knots, yields for S3. Next, we apply linear extrapolation to the knots at both ends, which yields. We tabulate the given fk's and computed results, delta fk and sk's. Then we calculate a's using the following equation as follows. Note that bk's and dk's are. We compute ck's using the following expression. Now that we have computed all coefficients, the cubic splines are constructed as follows. The interpolations for any x in the interval from xk to xk plus 1 are obtained by simply evaluating ykx. X equals 1.2 corresponds to the first interval, so we apply y1x to estimate y11.2, which gives 22.984, which corresponds to the true value of the function. X equals 2.1 corresponds to the third interval. We estimate f2.1 using y3x, which leads to 96.928. This value also corresponds to the true value of fx. X equals 2.9 corresponds to the fourth interval. We use y4x to estimate, which also results in the true value of fx. The discrete dataset was derived from a third-degree polynomial without rounding. Hence, when the cubic splines are expanded and simplified, they all give the true function. Likewise, the first and second derivatives can also be calculated for any x as follows. On this note, we conclude this video session. That is all for now. See you next time with another topic. Bye.